Okay, I welcome you guys all to Physics Unveil. My name is Franklyn, Einstein, and today we'll be talking about a very important topic, which is the linear charge density. Now, we've discussed the surface charge density, and now we're entering into the linear charge density. And from the name, you observe that for surface charge density, we are discussing about area, right? Charge per unit area. Now, for the linear charge density, we're talking about length per unit, or charge per unit length actually. So now, how do you know when we have a linear charge density or a surface charge density? It's very simple. The question will be so straightforward. Any question you see like a straight wire or a long wire, your mind should go into using the linear charge density equation. And now, what is the formula for linear charge density? The symbol is lambda equals to charge over length, where the length is the length, where the L is the length of the wire. Now, how do you impute this equation now into the electric field equation? Because for surface charge density and for linear charge density, our aim is to extrapolate it from the electric field. So now, we know from Gauss law, electric flux is electric field times area, right? And this is equal to charge over the permittivity of free space. Now, for the area, what kind of area are we talking about? We're talking about the area of a cylinder, because a wire in physics, we assume a wire to be in the shape of a cylinder. Now, what is the surface area of a cylinder? The surface area of a cylinder is 2 pi RL, where R is a radius, and while L is the length. Now, if you impute this in this equation, you have E multiplied by 2 pi RL equals to charge over what? The permittivity of free space. Now, if I make electric field the subject formula, I'll have that E is equals to charge divided by 2 pi RL epsilon naught. And if I rearrange this very well, I'll have charge divided by 2 pi epsilon naught RL. Now, you can notice something here. We can kind of separate this fraction to give us 1 over 2 pi epsilon naught R times Q over L. And we all know that charge over length is what? The linear charge density. So this is 1 over 2 pi epsilon naught R times the linear charge density. And when you combine this together, you have that electric field E is equal to the linear charge density divided by 2 pi epsilon naught R. So now, this is the equation of electric field when you're dealing with linear charge density. So now, let's look at a question to solve so we can know how to apply this linear charge density in a question. So, going to question 1. The first question, we see that a straight wire of length 2 meters carries a total charge of 6 microcoulomb. What is its linear charge density? That's the first question. And what is the electric field at a point 1 meter away from the wire? This is very simple enough. So the first step, write our solution, right? And the parameters given, a straight wire. So whenever I say a question on a straight wire, your mind should be going that, okay, I was expecting linear charge density. Then if you're lucky enough, then you say a question like that. Alright? So of length 2 meters. So now our length given to us, L is 2 meters, right? What is given to us? It carries a total charge of. Now our charge Q is equal to what? 6 microcoulomb. And because microcoulomb is not unit of charge, instead coulomb is unit for charge. We convert this micro to normal coulomb, which is 6. Micro is times 10 to the power of negative 6. Alright? So now that is what gives to us. Now, what is its linear charge density? That is lambda, so we ask for lambda, and then the electric field. Now, for linear charge density, which is the charge per unit length of the wire, right? So the charge is 6 times 10 to the power of negative 6, all divided by the length is what? 2 meters. 2, that will give us what? 3 times 10 to the power of negative 6. Now we can guess the units for linear charge. It's simple. Charge is in coulomb and length is in meter. So the unit for linear charge density is coulomb per meter. That is coulomb per meter. And that is the answer for linear charge density. Now moving on to the electric field. Now remember, the electric field for a straight wire is written as the linear charge density, all divided by what? 2 pi epsilon naught r. Am I correct? Now what's this r now? This r is a point 1 meter away. So the points away from the wire is also our radius, right? Because remember, our r could be the region where the electric field is being emitted at. So the electric field is equal to the linear charge density is 3 times 10 to the power of negative 6, all divided by, this is 2 pi. Then our epsilon is a constant, is 8.85 times 10 to the power of negative 12. And our r is what? Is 1. If you multiply this, you get electric field as equals to what? Approximately 5 times 10 to the power of 4 Newton per coulomb. Approximately, actually. That's my approximate answer. I'm sure if you punch your calculator, you get something quite a little bit different from this. This is just an approximate answer. So this is some kind of question. Remember very well. So a straight line, a straight wire, we have to use linear charge density, right? Because the linear charge density is charged by its length. So anytime you see the straight wire, your mind should go towards linear charge density. So this is how to solve this kind of question. So now let's move on into question 2. Says a 4 meter long uniform charge rod has a linear charge density of 2 times 10 to the power of negative 6 coulomb per meter. What is the total charge on the rod and the electric flux through a cylindrical Gaussian surface that encloses the rod? So our solution is 4 meter long. I'm giving the length now, right? The length is 4 meter, right? And it has a linear charge density, which is what? Lambda, as what? 2 times 10 to the power of negative 6 coulomb per meter. What is the total charge? Q, alright? And the electric flux. Okay? Simple enough, right? So now for the total charge, we know that linear charge density lambda is total charge over the length, right? So therefore, the total charge, making the solid formula, will be equal to the linear charge density times the length. And that will give us the linear charge density is 2 times 10 to the power of negative 6, and the length is what? 4 meter. I'm multiplying that, so the charge is equal to what? 8 times 10 to the power of negative 6 coulomb. So this is the answer for this first question, right? Making charge the solid formula. Now moving on to the electric flux. Now, remember from Gauss law, electric flux is equal to the total charge over the permittivity of free space. So therefore, the flux will be equal to the total charge is what? 8 times 10 to the power of negative 6 divided by the permittivity of free space has its own value, which is what? 8.85 times 10 to the power of negative 12, right? So therefore, the flux will be equal to, dividing this by this, we're having 9.04 times 10 to the power 5 Newton meter squared per coulomb. This is the answer I'm getting from the head calculation, right? So make sure you cross-check your calculation. So this is how to solve this kind of question. As you can see how we relate and we join all the points together. So we're asked to find what? The total charge. And we can find the total charge from the formula of linear charge density. So this is how we get some question. Then from flux, then our flux is equal to what? The total charge over what? The permittivity of free space from Gauss, which is known as Gauss law. Alright? So now you should know the kind of formula or equation to use for a particular question. Obviously, we know that flux also is electric field times area, right? We're now getting the area and electric field from here will be a lengthy calculation. Therefore, we can just use the charge over the permittivity of free space as our answer. So this is the kind of question you should expect in your test or exam, and this is how to walk this through. So let's move on into the last example, and we can say ourselves that I know linear charge density well. So the next example will state that a uniform cylindrical rod carries a charge of 5 coulomb and a linear charge density of 40 coulomb per meter. What is the length of the rod? The question is quite straightforward, right? So our solution, okay. Now it carries a charge. So your charge, our charge is 5 coulomb, right? And linear charge density, which is lambda, as what? 40 coulomb per meter. What is the length of the rod? Simple enough, because linear charge density is charge over length. So therefore, making length subject formula, we get that length is equal to charge over linear charge density. And that will give us what our charge? Charge is 5. And what is our linear charge density? 40, right? So that will give us what? 1/8 meter, or you can leave it in decimal number. Alright? So this is how to solve this kind of question. So I'm sure by now we have learned how to solve linear charge density. We have learned how to solve question on surface charge density. If you have learned these two, I can tell you and I can assure you that you're good to go in any exam, in any test, in physics, especially the tests based on electricity and magnetism. Right? So this is all for today. If you have any question, drop it on the comment section and I will answer it. Alright, so my name is Franklyn Einstein, and I'll see you in the next video.